Good morning, everyone.
Good morning.
Has anyone checked to see if Swivel's up this morning? Still not? I think you guys crashed Swivel. I don't know what happened to Swivel, but... So I'll repeat my announcement in case my email got to you into your spam box instead of into your inbox. That by tomorrow, if Swivel is not back up and you have not downloaded your data from Swivel, then you'll have to use the Many Eyes website instead. Many Eyes is very nice. They've got a nice search engine, so you can go and search on the same topic that you've already picked for Swivel. You can wait a little longer to see if it comes back up. They sent me an email saying they hoped early this week it would be up. And we'll see. The other thing is I had created a web page on the wiki, a separate wiki page for you to upload your data set or the link to your data set. And I don't know how many of you used it, but someone in the class deleted it accidentally. I think that's the problem with wikis, is that anybody can edit it. So if you put your information under this separate page, it's gone. And so you can instead go to the front page of the wiki and just add it as a comment, which is what many of you did already. So don't worry about it. I assume you still have your link, so just go and repost it again. And we're in this trying new technologies phase, and I guess allowing over 100 people to edit a wiki is maybe not such a good idea. So just add your link as a comment if it was on the second page in the wiki and has since been lost. Okay. All right. Are there any questions before we get started? I wanted to make one other announcement about the reading assignment, and that is I've more finely tuned the reading assignment, so if you go and take a look at it, I'll be updating the reading assignment under the syllabus link regularly, and I've extracted some of the parts from the reading assignment for this week, so it's not quite as long. I took a couple sections out. So if you want to take a look, you're welcome to read the entire last section of this chapter on making graphics, but I did extract 2 sets of about 8 or 10 pages. So today we're going to take a look at studying relationships with scatter plots, where we've got 2 quantitative variables. Did you have a question? Okay. In particular, we're going to look at 2 questions. Do average height mothers tend to be with, in other words, parent, with above average height fathers? So that takes a little bit of parsing. That's one question. Do 10,000 rats produce more heat than 1 elephant? So those are the 2 questions we're going to look at today, and we're going to study them using plots. So we're going to look at the relationships between quantitative variables. In the first case, to address the first question, we're going to see if there's a linear association between the heights of mothers and fathers in the Kaiser baby study. And for the second question, we're going to study the metabolic rate and mass of a whole collection of animals and look at transformation. We'll look at the relationship between them and what transformations would lead us to having a linear relationship between metabolic rate and the mass of the animals. And then finally, we'll get to another topic related to clear vision, which is the aspect ratio of your plots. And we will relate that to this studying the linear association and choosing transformations. Okay, you've already looked at, or many of you have looked at the distribution of height of the mothers in the Kaiser baby study. Here's the density plot for that. That's the green density plot. And the blue one is the density plot for the height of the fathers. So what's missing here is the connection between the mothers and the fathers. In the density plot on the left-hand side, there are all of the mothers. And so, for example, there's some fraction of the population of mothers have heights of about 60 inches. But you don't know where their partner is in the blue plot on the other side. So each of these are very nice univariate or one variable summaries, but they don't get at the connection between the mothers and the fathers. So let's take a look at a little bit of the data. So we saw that we could make statements about the distribution of heights of mothers and heights of fathers by looking at these density plots, but we can't see how the mothers and fathers' heights vary together. So this is just the top 6 rows or cases of the Kaiser baby. The first case, so in this particular instance, a case is a family. There's the baby and the baby's mother and the baby's father. We have collected information about the baby, such as its gestation and its birth weight. And we have collected information about the mother, such as her height and weight and education and smoking status. And similarly, we've collected information about the father, such as his height, weight, education as well. Notice that the third case shows a mother that's 64 inches tall, weighs 115 pounds, and the father's information is missing. Same is true for the fifth case. In fact, a lot of the father's information is missing. Why do you think the father's information, more of it is missing than for the mother? Yeah?
Maybe because when they were taking all the measurements, maybe they put that over the single mother.
Right. Maybe when they were entered in the study and being studied, the mother was clearly there because she was the one who's pregnant with carrying the child, and the father might not have been present for one reason or another, and therefore the information could be missing. So what we're going to do is we're going to take the pairs now of height for the mother and height for the father and take those pairs and plot them. So for the first one, it's 62-65. For the next, it's 64-70. For the next one, we will not be plotting it because the father's height's missing. Then it's 69-68. And the next one's missing, and then 62-64. And here's the plot. So the horizontal scale is the mother's height. The vertical scale is the father's height. And I have a question up there for you. Why are there so few data points? It's true that there are a lot of fathers have missing, but there are only about 100 or so data points in this plot. And there really were many, many hundreds of fathers and mothers that have weights. Were you going to say something? The data is repeated, meaning
like some of the points are the same.
some of the measurements are the same because your height was reported to the nearest inch. And so all the mothers that are 60 inches tall, 60.2 inches tall, 60.3 inches tall, et cetera, all go to 60. And so there's undoubtedly a lot of overplotting, meaning the circle, pick any one of them, one of these dots at, say, 60 and 70. So where the mother is 60 inches to the nearest inch and the father 70 to the nearest inch, there might be many parents, pairs of mothers and fathers being plotted at that location. So we can do something in R to help us see more of the data, because you don't know if there's a lot of people where the mother's above 65 inches tall, and you just can't tell in comparison to there being a lot of mothers that are roughly in the 63-inch tall group. What we do is we jitter. So we add a tiny bit of noise to all the measurements, such that random noise. And I also shrunk the dots so that there would be less overplotting. And so by jittering, adding this little bit of random noise, that's actually what I'm plotting here on the, I purposely did not label the axes nicely so that you could actually see what it was I was plotting. I was plotting a jitter of height by 2. So jitter is a function in R. Height is the variable, and 2 is another argument to the function jitter, which says how much little random noise do you want to add. And I experimented with it until I got something that looked like a, you can still see the sort of gaps, sort of vertical and horizontal gaps, but it looks more like how you would imagine heights of mothers and fathers to look like. So now we see a point cloud. And does it look like there's some kind of association between the height of the mother and the height of the father?
Yes.
You see it? Why do you see that? Where do you see it?
I think that there's a positive correlation. There's more, if there wasn't a correlation, we would expect the density of like these little points to be roughly analogous over this entire like square. But if there isn't, or if there is a correlation, we would expect it to sort of have a thicker density along the middle, right, where we could theoretically draw this straight line, and there would be more points at the upper right and lower left than there would in the other corners.
So if I'll paraphrase what you've said. You said that if we expected no relationship between the mother's height and the father's height, it would be, well, it is a blob, but it would be a more amorphous blob. Whereas if there was a positive association between mother's height and father's height, we'd expect that there might be, the taller women might be married to the taller men. And to help us see whether or not that's the case, I've added these little gray lines where the vertical line is located at the mother's average height, and the horizontal line is located at the father's average height. Now, the mother's average height is 64 inches, and the father's average height is 70. And so my original question was, do you expect that above average women tend to be married to, or partner with, above average men? And reciprocally, do below average height women tend to be partnered with below average height men? So that would say that you'd expect to see more points in which of those quadrants? There's 4 quadrants up there. So the top right and the bottom left, that you'd expect that to be where most of the data are. And I think that's roughly the case. It's definitely not exactly the case. So the association between mothers and fathers' heights is not a really strong association. We measure this association through what's called a correlation coefficient, and we'll be talking more about that on Friday. But for now, the correlation coefficient ranges between a -1 and a +1. When it's positive, that says that there's a positive association or a positive linear association, which means above average values of the variable in the horizontal axis is associated with above average values in the vertical axis. So in other words, there's a tendency to go move upwards. A negative association goes the other way. It would say that above average mothers' heights, mothers with above average height, tended to marry fathers or partner with fathers who were below average height. And that's definitely not what's going on here. Yet there's not a really strong association. Yes, question? Oh, okay. the question is, what's the range of correlations which would be a strong association versus a weak? And my answer is in some sense, it depends on the application. So biological applications, you like strong associations to be, this is all rough, to be sort of above 0.7 or something like that. Social scientists are really happy with a correlation of 0.34. So it really makes a difference as to what your application is. So that doesn't mean that there isn't an association. It just means that it's weaker than if it were 0.6 or 0.8. And you had a question as well?
Every time you use jitter, will it give you a different graph? For example, if you were in R, you did...
Yes. Every time you use jitter, you'll get a different plot because jitter's adding a little bit of random noise. But it's just a little bit, so the basic structure should still come through. So if I executed the exact same code again, it will not be the exact same plot. So here's our 3 pictures of data that I've fabricated where I know there's a linear association, and I've generated the plots of points and measured the correlation coefficient. And just, I took off all the X and Y labels because they've all been scaled to have roughly the same spread. And I would just want you to notice that on the left-hand side is a 0.975. So it's very close to 1. But when it's actually 1, all of the points will fall on a line. And so this is what a 0.975 correlation is. A 0.75 is the middle one. And a 0.45, which is similar to the correlation that we got for the mother's heights and weights, or excuse me, the mother's and father's heights, is the rightmost one. So that gives you a sense of what these scatter plots of 2 variables will look like for different correlation coefficients. Any questions? Yes?
So the correlation for that mother's height thing was 0.45?
No, it was 0.34.
Okay.
So it was even weaker than this.
All right.
Right.
I was just going to say, because that's drastic.
I think it's not
if we
so
could say-
drastic. One thing is, I'll say this. That point that's at the top kind of maybe makes you think it's a little stronger than it is. But there is a 0.1 difference, which is not insignificant. Question? No? Yes?
How do you find R values?
We're going to talk about that on Friday. Don't worry about it for now. Well, in R, you use the function COR for correlation coefficient. But we're going to show the actual calculation on Friday. There are other types of associations between 2 variables than a linear association. And so what I've generated here are some essentially just there's no fluctuation in terms of errors. There's just a function where I put in an X and I get out a Y and I look at the association. And then I can look at transformations that arrive at a linear association between these 2. One of them we kind of saw on Friday with the Intel chip data and the number of transistors over time. And we saw that was shooting up really quickly. And when we took a log transformation, it looked much more linear. Here's an example where we see the actual functional form between X and Y. We see that Y is 2 to the X. So that's like X is, if X were time, it would be something to the effect of the amount Y is doubling every year or something to that effect. And if we plot X against Y, we see a very steep curve. If we take logs of both sides, we have the log of Y is equal to the log of 2 times X. And that's a linear association. It's linear between the log of Y and X. So this log transformation says if I take the log of my Y values, plot them against my X values, I will then have a linear relationship between log of Y and X. Everybody clear on that? Sometimes especially in biological applications, we get examples where we transform both the y and the x variable. Those are log-log transformations in order to get a linear association between the two variables. So the plot on the left is the original data, and we see it's increasing as before, and we would naturally say, why don't I take a log of this? So now in the middle, I have plotted the log of y against my original data. You can sort of you can see that in notice the vertical scale. There are equal. Well, they're not quite equal. You see it goes from 2 to 200, but you see where 100 is? 100 to 200 versus 20 to 50. So that scale is log scale on the y-axis. And when we've made that transformation, we still have a curve in our data. It's going in a different direction, but we still have a curve. So I take the log of the x variable and plot a log-log transformation, which is log of y against log of x, and now I have a linear transformation. Okay. So in part, when we are making scatter plots and we think about these issues of clear vision and clear understanding, one of the things that we're shooting for is to fill the data region with our data and to not leave a lot of empty space. And in a way, making these transformations helps us see the data and at the same time uncovers the structure or the relationships between our two variables that we're plotting. So here's our next example. This question was actually came from a study by Kleiber in 1947. Or Kleber, I don't know how you pronounce his name. He asked, does a horse produce more heat per day per kilogram of body mass than a rat? Okay. So to study that, he looked at two variables. He looked at the mass of an animal and the metabolic rate of an animal, which is the heat production per unit time. And he measured 19 animals: a mouse, a dog, a cat, a rat, a goat, a man, a cow, an elephant, and a sheep, and a few others. And his data he published with his study, and I was able to extract the data. And here it is. There are 19 points here for these 19 different animals, and we have plotted the pair of mass and metabolic rate. So what would you do with these data in order to be able to see the data, see the relationship between mass and metabolic rate?
Jitter.
Ellie? Jitter? Yes, there's a lot of overplotting there. Not a lot. You've probably seen 9 points, and we know that there's twice as many. So we could jitter. What else could we do? Yes? Take logs on the y-axis. Why? Because we see one really large value, and taking logs brings in those values and spreads out the smaller ones, right? And so if we try that, I actually took logs of the y and logs of the x. If I had shown you a plot of just the log of the y and not x, it would have looked like the middle plot that I just showed you. There would still be curvature in it. So this is both log of metabolic rate and log of mass plotted against each other. Now notice I didn't need to jitter now because it stretched out my scale in such a way that I can now see my observations. So these are Kleiber's 19 animals, and now you can see that it has a very high correlation. There's a very strong linear association between the log of the animal's metabolic rate and its mass. I did log base 10 so that we could have, so it could be easier for us to sort of see when you go from a mass of 1 kilogram to 10 to 100 to 1,000, that you have a sense of the size of the animal. Does that seem surprising to anyone? No? So we're getting to try and answer a question. So before we get there, well, no, this is it. Here's the question, and I've actually added man into the equation as well. A man has roughly 70 kilogram mass and gives off about 1,000 watts in terms of heat for the metabolic rate. An elephant has a mass of 7,000 kilograms, roughly, and a rat, 0.7 kilograms. Which gives off more heat? 10,000 rats, 100 men, or 1 elephant, or all they about the same? You've got 2 minutes to talk to someone you're sitting next to and come up with an answer. Notice that these were very specially chosen animals. 100 men will come up to about 7,000 kilograms, and 10,000 rats will come to about 7,000 kilograms. I'm going to put the picture back here and allow you to talk for 2 minutes and come up with an answer. Go for it.
There's this strong correlation. Basically, if they have equivalent masses, they have equivalent metabolic rate. Look at this correlation. You could just do. Okay. So we need to look at the ratio of watts versus
Yeah, yes, it is. That's this relationship. The relationship between watts and kilograms is exactly this relationship. That's the vertical axis is your watts and the horizontal axis is kilograms. So what do you think? Yes?
I think the rats.
The rats?
The rats will produce more heat
Why do you think so?
because even though mass and metabolic rate are linear, are related. It says the lion has a slope of 0.75. So because it's not one, it won't increase. They don't need mass and metabolic rate. They don't increase at a 1-to-1 rate. So I think that. Does that make sense?
It does to me. Does it make sense to other people? He said that because the slope of that line is 0.75, that if you do what? If you take you take a rat's mass, and how do you get an elephant? You take 10,000 rats. That increasing its mass, scaling it by 10,000, you're telling me does not what?
I think it'll be 25% more.
Does not scale the its the elephant's metabolic rate does not scale by 10,000. So it's an important concept that I think it's best if we take a look at on the document camera. So roughly, we had a picture that looked linear in the log scale. So the log of mass and log of metabolic rate is roughly linear with a slope of 0.75. So what does that mean about the relationship between mass and metabolic rate? So we have log of metabolic rate is sort of some constant A, which we don't really care about, times 0.75 log of mass. It might be easier for us to think about this back in the original relationship without the logs. So if I were to unlog this, raise it, exponentiate it, I would get metabolic rate is equal to what, roughly? What are you going to say? Yeah, but, well, I'm exponentiating with whatever I've logged it by, right? So we can ignore the base. So it's some constant is what you're saying, right? Okay, so some constant, and then what else? Where does the 0.75 come in? It's an exponent, right? Because this is essentially log of mass to the 0.75, right? So this should be some sort of constants, which I'm not worrying about, mass to the 0.75. So what that says is if I've got a rat, and a rat produces 1,000, the metabolic rate of a rat is about 100, and this is the rat's mass to the 0.75. Now, if I take 10,000 rats, that's like multiplying both sides of the equation by 10,000, right? So that's 10,000 times 100, which is 10,000 rats. But that's not an elephant's metabolic rate. An elephant's metabolic rate comes about by looking at its 10,000 rat mass raised to the 0.75 is really different, right? This is an elephant's, which is about what? I don't remember what's the value? Was it 1,000 or 10,000? Man was 1,000, 100, I thought. No, 1,000, right? Do you see the difference between these? So here, that 10,000's inside my, is being raised to the 0.75, which is exactly the point you were making. So what is 1,000 to the 0.75? I don't know off the top of my head. Let me see if I can get that from R really quickly. So if we take 10,000, raise it to the 0.75, we get 1,000. Okay, so 10,000 rats produces a lot more heat than an elephant. So although an elephant is 10,000 times the mass, it only produces 1,000 times, right? So this is 10,000 to the 0.75 is roughly 1,000. So it only produces 1,000 times the amount of heat as a rat. Yes. Well, yes, that's right. It only produces 1,000 times the amount of heat as a rat, as a rat, whereas 10,000 rats has the same mass as an elephant, and it produces 10,000 times the heat of one rat. Does that make sense? Have I confused too many of you? Yes?
How would we go about calculating that constant, or is that irrelevant?
It doesn't really enter into this, but you could. You could Well, first we have to figure out what A is, right? So whatever A is, we can, so if we, here, let me get a clean piece of paper. What's it, you see it already?
Just pick 2 points.
Yeah, or when we exponentiate, we get, this is what someone was saying, this is what you were saying at the beginning. If we have log of MR equals A plus 3/4 log mass, if we exponentiate this, we get MR equals exp of A plus 3/4 log mass, which is, I can now make that a product, right? So that's e to the a or 10 to the a or whatever, mass to the 3/4. So that's the constant that we're saying we don't worry about. Okay. So it's essentially what we wound up observing was because of this 0.75, that says that although one elephant is equal to 10,000 rats in terms of mass, one elephant produces much less than metabolic rate, much less heat than 10,000 rats metabolic rate. Okay? Question? No? So scientists were saying, you know, that's great that you came up with that 3/4, but I really think it should be 2/3. Where does the 2/3 come from? Two-thirds comes from this relationship between mass and length and between metabolic rate and length. So let's think about mass. And there's the mass of an animal of length L. So L is the length of our animal. And in fact, we treat all our animals as sort of spherical. Here's my spherical cat. Okay? My cat has a mass of 5 kilograms and is about, it's got dimensions that are roughly 10 centimeters by 30 centimeters by another 10 centimeters or so. But I'm going to treat my cat as a sphere.
Is this the imagine a spherical cow?
Similar to that, that's
thing?
right.
Right.
So what's the connection between mass and length if we have a sphere? So roughly mass is proportional to volume. And if I've got this sphere, what's volume in terms of length? What's that? So I can't see who's talking. In terms of L, what's L is our length? So what's volume? Is area times length, and what's area? Length squared. So it's, thank you, so it should be proportional to L cubed. On the other hand, metabolic rate, do you have a sense as to what that should be proportional to? That's giving off heat. Why do they tell you if you're cold that you should wear a hat? Yes? Surface area. So that should be proportional to surface area. And what's that in terms of L? Thank you, L squared. Okay, so that says that we should be able to figure out what's the relationship between metabolic rate and mass. So if metabolic rate is proportional to L squared, well, L squared exactly equals L cubed to what power? 2/3. And that's proportional to mass to the 2/3. So that's telling us now you can also see where that log-log relationship comes from. If I take log of both sides, I get the log of metabolic rate is roughly proportional to 2/3 log of mass. And that's where that log-log relationship comes from. And it says that my coefficient for the slope of that line should be 2/3. And instead, it's 3/4. So this was in 1947 that this guy, Leiber, found this relationship. And since then, biologists have continued to study this relationship. So here's our answer, is that 10,000 rats give off more heat than 100 men, and 100 men give off more heat than one elephant. And as was pointed out, it's the slope. And there's the equation. And y 3/4 we just talked about. And the biologists have continued to study it. In 2010, Clark and 2 other scientists collected data from 550 animal species and plotted the log of the metabolic rate against the log of the mass, and they still found a linear association with a slope of about 0.72. And so the biologists are coming up with various theories. It's still not sure whether it should be 3/4 or not, but there are now theories in terms of with a mouse or a rat, all of its cells are close to its surface, whereas with an elephant, many of its cells are further away, and some sort of fractal dispersion of heat might make it such that it's not 2/3, but it's 0.7. So there's still ongoing research in this topic. I want to know, what's that one animal up there? Maybe that's a typo in there. Again, this data was available with the article. If you want to search on Clark 2010 and the metabolic rate and mass of animals, you'll find this data available on the web. So essentially what we've done is we've used clear vision to uncover the structure in the data. So by taking these transformations, we've been able to see our data better, and that's also told us or indicated what kind of relationship there is between our various variables. So this is related to the aspect ratio of a plot, which is the height of the data rectangle over the width of the data rectangle. And it's very important for us humans in terms of perception to judge rates of change by having an aspect ratio that's a particular ratio, which is essentially a 1-to-1, or it's called banking at 45 degrees. So the aspect ratio affects our ability to decode rate of change. There have been experiments done to sort of figure out what aspect ratio allows us to decode a rate of change best. And in particular, banking at 45 degrees was found to be the best angle. And what that means is that if we, let me show you the next plot. I'm going back to the original fake data. And if I just connected the dots with little line segments and looked at the orientation or the angle of each of those line segments, take their absolute value, and then think of those as a collection of angles or a collection of absolute values of angles. And if roughly it's centered at 45 degrees, that's where people can best determine a rate of change. And so if you look at these, the one on the right-hand side, they're all roughly banked at, all the line segments connecting the dots are banked at 45 degrees. And so transformations that improve the aspect ratio also uncover the structure of the relationship between the variables. And it's much easier to see important features. We're going to continue looking at this on Wednesday. And at this point, what I'd like to do is go back to the story that I promised you on Friday, and we didn't have a chance to see. And we've got about 4 minutes left. So really quickly, let's look at Napoleon's March. So as a little bit of background, Napoleon started his march in June of 1812, and he was planning to march to force Alexander I to submit to the terms of a treaty that he had signed 4 years earlier. So he decided to take the fast northern route to Russia. Napoleon's Grand Army had about 600,000 soldiers in it, half of whom were French, and the other half were sort of hired-on soldiers from other states that they had, Napoleon had taken over. In contrast, the Russian army was much weaker and smaller. There was the Cossack cavalry, which only had a few tens of thousands of soldiers in it. Altogether, there were about 150,000 soldiers in the Russian Imperial Army. And they knew they could not defeat Napoleon by direct confrontation. So they designed a defensive campaign of strategic retreat. So they never engaged in an actual full-out battle. They just retreated slowly, kept pestering him along the flanks of his army and falling back and destroying the land as they fell back. And they did this very slowly. And so by September, Napoleon's forces were reduced by about 2/3 without having ever engaged in a single pitched battle. They had lost so many soldiers because of fatigue, desertion, hunger, and the raids by the Russian forces. At this point, they were very close to Moscow, and the Tsar insisted that the Russian army engage with the Napoleon's army. And that was the battle at Borodino Field, and no one came out as a clear victor, and the losses were tremendous. 108,000 soldiers died on both sides combined, and neither side had a decisive victory. The Russians withdrew, and at this point, the Moscow citizens fled the city, and the Tsar fled as well. So Napoleon arrived in Moscow to an empty city with no supplies. Within a few days, fires broke out. The city was, many of the structures were wood. Fires broke out and destroyed most of the city. And Napoleon waited for the Tsar to return, and it kept getting, time was passing, it kept getting colder. There were no supplies, no place to stay warm. And finally, he gave up a month later in mid-October when winter had started, and he began the march home. The Russian army was ready for him, and they blocked the southern exit out of Moscow. So they had to go back the way they came, the northern exit. And the Russian army continued to follow them and harass them as they made their way back to Paris. They retreated the way they came. There was little food left, and they were followed by the Cossacks. Here's a depiction of the night bivouac of the soldiers on their way back. There was one particular crossing of the Berezina River that was particularly dramatic, where you can see there are horses and soldiers that are being floated downstream. They lost, again, about 2/3 of their soldiers that were left in just this simple river crossing because of the temperatures. 50 years later, Charles Menard made a graphical representation of Napoleon's march. And his graphical representation is considered one of the best graphs ever produced. He looked through all of the diaries of the soldiers and collected statistics, and he condensed a huge amount of information into one very simple form, which is Menard's rendition of Napoleon's march. Notice that what he's done is he's placed the data on a map, roughly on a map. The width of this sort of stream corresponds to the number of soldiers in Napoleon's army. And as you see them progress across to Moscow over there on the right. That's the beige band. And the black one coming back is the return route. And you can see where parts of the army would branch off and then meet up later on. And you can see how as they progress across to Moscow, the band gets smaller and smaller as they're losing all of their men. You can even find the river crossing of Berezina is right there. Let's see if I can, where you see the river and the size of the little black band decreases to about 1/3 of the original size. Along the bottom are the temperatures and the time at the particular times where the army was. You see the line up to during its return. You can see how it's getting colder and colder and colder as they're coming back. And just to leave you with a couple quotes, it's was said that his graph seems to defy the pen of the historian by its brutal eloquence. And that's it. See you Wednesday.